All right, so this is the lesson video for section 3.1 for AP Calculus AB, and this is the beginning of really what we're going to be doing for the rest of the semester, which is dealing with derivatives. So today we're formally going to talk about the definition of a derivative, and I know I mentioned when we went through section 2.4 that there was a lot of derivative information in there, and there really was. They just weren't calling it a derivative in your book. They were calling it an instantaneous rate of change, which is the same thing. So today we're really going to focus on the derivative as a function, and rather than working through a lot of those definition of derivative questions again, I'm going to put more focus on what's happening graphically and how we describe what the derivative means in terms of the graph of the function and the graph of the derivative of the function. Okay, so just as a quick review, this is what was in 2.4. We had the whole idea of the slope between 2 points. So here we're using the points P and Q. And if I find the slope between those 2 points, I can rewrite this. Notice it's f of x plus h minus f of x over x plus h minus x. So this is the same as f of x plus h minus f of x. So my change in y, and then my change in x is just going to simplify down into h. So that's my average rate of change. And like I mentioned before, if I take the limit as the distance between those two functions approaches 0, now I'm taking what was an average rate of change and turning it into an instantaneous rate of change, or, like I said before, the derivative. Okay, so what you see right here, this is actually called the general definition of a derivative. So whenever we find the derivative of a function, and we typically won't do it this way, we're going to learn a lot of derivative shortcut rules, but whenever we find the derivative of a function, technically this is what we're doing. So we'll learn a lot of shortcuts for this, but you do have to know the form for the general definition of a derivative. Okay, so we've also got some other information here, just some vocabulary. So the whole idea of differentiation, when we are taking a derivative, it's called differentiation. So if I say to differentiate, that means take the derivative of the function. And if a function is differentiable, that means that the derivative exists. All right, so we also have some notation here. These are all different ways that I can write the derivative of a function. And all of these actually mean the same thing. So the ones that I'm circling in red here are the ones that you're commonly going to see in this class. F prime, y prime, dy dx, df dx, d dx of f of x, that means take the derivative with respect to x of whatever follows, in this case f of x. So these last two, these are more of kind of a multivariable calculus type of notation. When you see that capital D, that's also a notation for taking a derivative, and then the subscript is telling me to take the derivative with respect to x for that last one. So the ones that I have circled there, those are the ones that you really need to know moving forward. And you'll see these enough that you'll get comfortable with the notation. Okay, so here's just a couple of quick examples going through what we went through in section 2.4, which is the whole idea of solving the limit to get the derivative. So what we have here is f prime of x. We're trying to find the derivative of x squared. So you can see they've plugged into the form for the definition of a derivative. And when we solve these limits out, it's just like what we were doing before when we were solving limits. You start with direct substitution. If I substitute directly into this limit, I'm going to get 0 over 0. So I've got a simple polynomial function. And typically what's going to happen on these when we're taking the derivative is if I expand everything out, so I'm going to expand out the x plus h, it would be x squared plus 2xh plus h squared. And then I've still got that minus x squared. If I expand that out, then what I'm hoping is going to happen is that things are going to cancel out, and I'm going to be able to cancel out my h. And you can see that in this case, we actually can cancel the h. So these h's all go away. So in the end, I've got 2x plus h. When I take the limit as h approaches 0, that gives me 2x. So the derivative of x squared is 2x. And for those of you that know the power rule, you would have already known that that was going to be a solution. And we'll learn the power rule in just a couple more classes, and then you won't have to go through this process. But the main thing I want you to focus on is the idea that we're taking the slope between 2 points, and we're making those 2 points get infinitely close together. There's also another form for the definition of derivative, and this is the one that 2.4 primarily focused on, which is the derivative at a point, or the instantaneous rate of change at a point. So in this one, we're looking at f prime of a. So instead of saying the instantaneous rate of change or the tangent slope, we're calling it f prime of a. So it's the derivative evaluated at the point A. And notice that we're still doing a function value. We're doing the change in function value minus the change in the x values. So change in y over change in x. We're taking the limit as one point approaches the other. So we have a point at a, f of a. We have another point at x, f of x. And then we're getting the slope between those, and we're going to evaluate. So here they ask us to, they give us the function, and they want us to find f prime of a. Now, when we do that, you can see that this is going to work out a little bit differently, and you can see what the result here is. But if we were going to solve this one, again, you have to go back and think about what we did with limits. Here, if I plug in a, I'm going to get 0 over 0. So when we were doing limits, in a situation like this, we would have gone through and we would have multiplied by the conjugate. And this is what I would have done. So square root of x plus square root of a. Remember, I can do that because I'm essentially multiplying by 1, which isn't doing anything but changing the form of the function. And in the end, what this will simplify down to is the limit as x approaches a of x minus a over x minus a times square root of x plus square root of a. Okay, and then you can see the x minus a's are going to cancel out. And then essentially what I have here, when I take the limit as x approaches a, is I have 1 over 2 times the square root of a. And from there, now if I want the derivative at some particular a value, like if I want f prime at 9, I plug the 9 in for the a, and you can see you get 1/6. Okay, so the question says, what does this mean? Well, what that means is the instantaneous rate of change of my function where x is equal to 9 is equal to 1/6. So that is the tangent slope of the tangent line to my function at x is equal to 9. Okay, so here's another example. We've got x squared plus 2x plus 1. It says find f prime of -3. So what I want you to do is just take a second and pause the video and solve that one out for f prime at 3. Okay, so here's what you should have ended up with on that one. I didn't show all of the algebraic steps, but what will happen here is if I add up all of my constants, I can factor it again. The x plus 3 will cancel, and in the end, I'll get a value of -4. So it's not that difficult to do. And like I said, my primary focus today is not going to be all this algebra because we did a lot of these in 2.4. My primary focus is going to be what we do the rest of the time here, which is primarily focused on what's happening graphically. Okay, so taking a look at the graph of a function and its corresponding derivative graph. What I want you to do, these two graphs are side by side. I want you to compare what's going on in these two graphs. Keep in mind what f prime is going to mean. F prime is going to represent the slope of the tangent line to my function at that point. So, for example, let me circle some points here so you can see which ones I'm talking about. When I'm at the point A, notice the slope there is 4. The y value here is 4 for A prime. So the slope on the original graph matches up with the y value on the derivative graph. That's really important to remember. Look at the point where we're at C. So I've got a tangent slope of 0. Notice that the derivative graph has a y value of 0 at that point. Also, let's say we're looking at E. See how we have a negative tangent slope there. You can see over here, E prime, we've got a value for the derivative function there of -1. So again, representing a slope of -1 on the original graph. Okay, so that's the main relationship that we're going to be looking at. When you see a positive slope, you should see a positive y value on your derivative graph. When you see a negative slope, you should see a negative y value. And when you see a 0 slope or a horizontal tangent, you should see a value of 0 for your derivative graph. Okay, so let's take a look at matching some graphs with their derivatives. So what I have here are 4 functions, and down below, I've got 4 derivative graphs. And what we want to try to do is match up the function with its corresponding derivative. Now, really what we're doing here is we're just thinking about increasing and decreasing. We're thinking about 0 slopes. So those things kind of like what we looked at in the graph above, but it's a little bit harder now because we've got to look at these separately and kind of estimate which one's which. So when I look at that first function graph, this one right here, when I look at that first function graph, I'm thinking about the fact that that function is always increasing. Since that function is always increasing, that means I should always have a positive slope. That means the y values always need to be positive. Well, looking at that, I've really only got two options here, either A or B, right? Those both have y values that are always positive. Well, I know it's not B because B is indicating that I have a constant slope. That would be what my function's derivative would look like if I had a linear function. But we have slopes here in this graph that are changing. It starts out really steep and then it's flattening out. And you'll notice that graph A, that's actually what's happening in graph A. We start out with these really steep slopes and then it's flattening out over here and becoming closer and closer to zero. So I know that this one is going to be A. And I'm going to go ahead and cross out A because we've used it. All right, now let's look at the second graph, which is that absolute value graph. Notice to the left of 0, we have a slope of -1. To the right of 0, we have a slope of 1. That's a graph you should be very familiar with. Well, looking at these derivative graphs, that one's pretty simple, right? I can tell that that's going to be C. I guess I just lost my information here. But I can tell that that's going to be C. And the way that I can tell that is because on that graph of C, I have a -1 value for the function, for the f prime, and then I have a 1 value to the right of 0. Okay, so let's write down C for this one. All right, now let's move on to the next one. We've got a linear function here. When we have a linear function, that means we should see the same slope value anywhere on the interval that I'm looking at for my domain. Well, the only one that has the same slope all the way through is graph B. So I know that this graph is going to match up with derivative graph B. And then just by default, I can see that the last one, this one's going to have to be D. But you can also look at the fact that this one has a negative slope until I get to 0, and then a positive slope after. And you can see that same behavior at graph D. Okay, so that's kind of the main idea when you're matching these things up. You can look for places where you have 0 slopes. You can look at increasing and decreasing. But really what you're wanting to think about is, how does the derivative graph relate to the graph of the original function? Okay, so take a look at the graph that we have here. It says graph the derivative for the function shown below. And what we're looking at is an absolute value graph that's been reflected and translated. And what I want you to do is try to graph the derivative of that function on this blank graph that you have to the right here. So I want you to pause the video and I want you to try to graph the derivative, what it would look like. So pause the video, and when you come back, I'll show you the solution. Okay, so here's what you should have ended up with. You can see to the left of -2, we've got a slope that's actually positive. If you read the graph from left to right, you can see I have a slope of +1. And then to the right of -2, I have a slope that's now -1. And you can see that now my derivative graph has this jump discontinuity where the derivative jumped to a value of -1. This actually gets into a little bit of the idea of differentiability. So keeping in mind that the derivative is a limit, at -2, there is no derivative value defined because the left-hand derivative would be 1 and the right-hand derivative would be -1. So since those one-sided derivatives aren't matching up, there's no derivative value that's actually defined. So you notice that I have the open circles right here, and I have open circles because there's no derivative value defined at -2. Okay, so let's move on and take a look at another example. So what we're trying to do here is we're trying to determine whether or not this function is differentiable. So we have this piecewise function where y is equal to -3x for x less than or equal to 0, y is equal to x squared for x greater than 0. So if we were to go through and try to evaluate the one-sided derivatives, so essentially what I'm thinking about is what's the derivative of each piece of this as x approaches 0? So as x approaches 0 from the left, I would be looking at the negative 3x rule. So when I take the derivative of that, what I'm going to find is that this is negative 3. And you can just kind of think through that one, or you can actually solve that limit out if you want. If you think through it, it's a linear function. It always has a slope of negative 3. For the second part of this, it's x squared. We already talked about the derivative here being 2x. So we looked at that exact function. If I evaluate that derivative at 0, it's actually 0. So the right side derivative is 0. The left side derivative is negative 3. Well, since that's the case, there is no derivative. The derivative doesn't exist at 0 because the left-hand derivative and the right-hand derivative are not the same. Okay, so that's that idea of differentiability. We're actually going to spend an entire day focusing on differentiability next time. So the next video that I post will be on section 3.2, and that's actually the title of that second section, differentiability. Okay, so a couple of examples here now. These are old AP multiple choice questions. And what I wanted to show you here is really what I need for you to know as it pertains to the limits with the definition of derivative. So what I need you to understand is, what are these forms and what do they mean when you see them? You don't necessarily have to solve these limits out, but what you need to be able to recognize is, oh, this is the definition of derivative, and they're either asking for the derivative function or they're asking for the derivative at a point. And you can see on this first one, we have sine of pi plus h minus sine of pi divided by h, limit as h approaches 0. So what I'd like for you to be able to recognize is that this is the definition of a derivative at a point. So ideally, what you should be thinking about when you see this question is that this is using the function sine x, and the question is really asking, what is f prime at pi? So that's really what that question is. And so I don't need you to be able to solve it right now, but I need you to be able to understand what the limit says. So knowing that that's the case, we're going to do this in a couple of weeks. The derivative of sine is cosine. The cosine of pi would be negative 1. So this one turns out to have a value of negative 1. Okay, so now I want you to do the same thing on the second one. Try to figure out what form is it, and then what are they asking you to do. So you don't necessarily have to get the answer, just try to figure out the form, what's the function, and what are they asking you to find. So pause the video and try to solve that out. Okay, so what you should have recognized is that this is the first definition of derivative that we saw. This is the general definition of a derivative. So we're looking at f of x plus h minus f of x divided by h, limit as h approaches 0. So I know here that f of x is actually equal to x cubed, and I'm looking for f prime at x. So that's what I'm trying to find. And it turns out for this one, again, you don't have to know how to do this yet, but if you knew the power rule, the derivative turns out to be 3x squared. Okay, so these are the main things that I want you to see. When you see those types of questions, that's how you should be interpreting it. You shouldn't be thinking, oh, I need to expand out x plus h, I need to cube that, and then combine like terms. That's not what I want you to do. I want you to recognize that that is the definition of a derivative. All right, and then this last page, I've got some questions here that I want you to try. And what it is, it's a graph with 5 points, and they're asking you about things with the average rate of change and instantaneous rate of change. So I want you to just take a few minutes, and I want you to try to solve these 4 questions that are in the notes. So go ahead and pause the video, and then when you come back, I will show you the solutions to these and just briefly explain them. Okay, so here's what you should have ended up with. So part A, it says, between which 2 consecutive points is the average rate of change of the function the greatest, and then also the least. So average rate of change is just secant slope, slope between 2 points. You can see that if I use A and B, that's the steepest positive slope I have. It's going to be the least, the lowest number if I have the steepest negative slope that I can find, which would be points C and D. For question B, is the average rate of change of the function between A and B greater than or less than the instantaneous rate of change at B. So what you want to be thinking about here is what would the tangent line at B look like? It would look something like that. And you can see that that slope is a little bit less than the slope between A and B. So that's where I came up with the solution for part B being the average rate of change is a little bit greater than the change at B. Okay, C, it says sketch a tangent line to the graph between D and E such that the slope of the tangent is the same as the average rate of change between D and E. So what we're trying to do here is we're trying to use that secant slope and we're trying to translate that line down to create a tangent line that is roughly parallel to the secant line. And you can see there I've got a tangent line and a secant line that are parallel. This is actually the mean value theorem, which we'll talk about later on. You don't have to know that right now. Okay, and then the last question, give a set of 2 points for which the average rate of change of the function is approximately equal to another set of 2 points. And there's a lot of different answers here. So I gave 3 groups, there may even be more, but I did A and C and D and E. I did B and C and A and E, or A and D and C and E. Like I said, there might be others, but the main thing is you're just looking at the slopes. The average rate of change is the slope between 2 points. You're trying to find equal slopes there. Okay, so that's everything for section 3.1. Like I said, the primary focus should really be on what's happening graphically, and then try to focus on, when you're solving those limits out, try to really focus on the forms that you get when you're writing out the definition of a derivative.